Hello everyone. In this lecture of the communication theory course, we'll be giving an introduction to analog modulation. We'll start with the definition of modulation and then why do we need modulation, and finally we will give a brief about some basic analog modulation types. In order to understand what is modulation, let's start with understanding what's a communication system. A basic communication system consists of three main components, and these are the transmitter, the receiver, and the channel in between. The purpose of any communication system is the transfer of information. So the sending node or the transmitter has some information that need to be transferred to the receiving side. Unfortunately, the link between the transmitter and the receiver, this is what we call the channel, might not be ideal. It might have many sources of impairments. One of the main sources of impairments in such a channel is what we call noise. Noise is in general any unwanted signal or any unwanted information added to the information that needs to be transferred from the transmitter to the receiver. And the main task of the receiver is to extract the exact information from the noisy version of the received signal. So again, the main purpose of a communication system is the transfer of information that is known at the transmitter and unknown at the receiver, and the receiver's task is to discover what is the exact information it is receiving. In order to make the task of the receiver easier, there might be some processing needed at the transmitter to make the communication process easier, to make the version that the receiver gets of the information signal is easier to interpret, and the likelihood to extract correct information from the noisy version is much higher. So what is meant by modulation? Modulation is one of the basic processes that usually happen in communication systems. And the main definition of the modulation is changing one or more of the characteristics of a signal, and we will know later which signal do we mean here. And the purpose is to make communication of information signals possible, or we can consider that the purpose of the modulation to make the communication process easier. For example, in the figure here, we might see a signal. This signal is a sinusoidal signal, and we might have this information m of t, and this is the information that we need to transfer from the transmitter to the receiver. So one form of modulation is to change the characteristics of this upper signal. This is what we call a carrier signal. So as you can see here in figure C, that we changed the amplitude or the envelope of the carrier signal to be proportional to the information message. If we look at the envelope here, the top points of this signal, they are similar to m of t. So we changed one of the characteristics of the signal in figure A. This is what we call a carrier signal in proportion to the information signal m of t, and the purpose is to make the communication of the information signal m of t more possible. Another form of modulation is changing the frequency of the signal. We can see here in figure D that while the amplitude remain constant or almost constant for the signal, the frequency is not fixed anymore. We can see here that we have relatively low frequency, while in the next part we have relatively higher frequency. So the frequency of the signal, of the carrier signal, is changing in accordance with the information signal M of t, and again the purpose is to make the transfer of the information signal M of t more possible. As you can see in both examples here in figure C and figure D, while we wanted to transfer the information message M of t, the signal that is actually transmitted or the signal that is actually transferred has a much higher frequency than the original information signal M of t. And you can easily see that from the period of the signal or the rate of change of the signal M of t, which is a relatively low rate of change, which reflects to a low frequency, compared to the higher rate of change in signals C and D here, the modulated signal or the signals after being modulated. That's why it is commonly accepted to define the modulation as frequency up conversion, or increasing the frequency of the signal to be transmitted. And in a while we will discover why we might need to increase the frequency of the signal. So the general definition of modulation is changing one or more of the characteristics of a signal to make communication more possible or more feasible. However, the most commonly used types of modulation involve frequency up conversion or frequency translation, shifting the frequency of the signal to be transmitted to higher frequency. So why do we need modulation? Why do we need to increase the frequency of the signal? Actually, one of the main reasons that we need to increase the frequency of the signal that is communicated is because of the practical antenna designs or practical antenna sizes. In order to radiate a signal, an electromagnetic signal, from an antenna, the size of the antenna should be proportional to the wavelength of the signal. And of course, we know that the wavelength is equivalent to c over f, where c is the speed of light and f is the frequency of the signal. So for an antenna to easily radiate a signal, or in the other side to receive an electromagnetic signal, the size of the antenna, that might be the length of the antenna or something like that, should be proportional to the wavelength of the signal. As a rule of thumb, we might say that the antenna size should be in the range of lambda over 4, where lambda is the wavelength of the signal. Let's consider a few examples of signals. Let's start with a voice signal. A voice signal, any voice signal, is known to have frequency components in the range of 300 Hz to around 3400 Hz. Sometimes we consider that the highest frequency in a natural voice signal is 4 kHz. So in order to send a signal, in order to communicate a voice signal whose frequency range is from 300 Hz to 3.4 kHz, we need an antenna whose size is proportional to the wavelength of such signal. So if we want to calculate the wavelength of such signal, that will be c over f, where c is the speed of light, approximately 3 times 10 power 8, and the frequency, let's consider the highest frequency of the signal, which is 3400. This calculation results in a wavelength of 88,000 meters. When divided by 4 to get an approximate antenna size, we find that approximately the needed antenna size is 22 kilometers. Of course, it would not be practical to have an antenna whose size, whose dimension, whose length is 22 kilometers. Of course, you might need to consider that when we need an antenna, that is the case when we have a sort of wireless communication in which we might need that the transmitter or the receiver or even both are mobile. That's why we don't want to be tied with a wire or something like that. However, if we decide to transmit a voice signal, such as what we do in phone calls, it would be completely impractical to send the signal in its original form, which has frequencies in the range of a little below 4 kilohertz, because that requires an antenna whose size is 22 kilometers. Another example, if we consider, for example, high quality music signals, similar to those which we hear in radio. So the frequency range of such high quality music signals is around 10 kilohertz. So again, using the rule of thumb in which we need the antenna size proportional to lambda over 4, we still need a very high size or length of the antenna, 7.5 kilometers. However, if we do modulation, if we use a communication system in which the transmitter processes the information by modulation, by frequency translation first, such as in cellular systems, in mobile communication systems, in which the information signal is transmitted using a carrier whose frequency is in that range. That range is 1.9 or 2.1 gigahertz. That's a relatively very high frequency compared to the original range of frequency of the signal. Consider a voice call in which the original information has frequency in the range of 4 kilohertz. However, we perform modulation such that the frequency content is translated, is converted to around the 2.1 gigahertz. In this case, the wavelength of the signal, again, that can be calculated as C divided by the frequency. In such a scenario, the required antenna size, which is proportional to lambda over 4, is 0.03 meters or 3 centimeters. So definitely that is a practical antenna size that can be placed in a mobile set, which is easily mobile and can be a handheld set to facilitate mobility. Without modulation, we wouldn't have been able to transmit the voice signal in such a wireless manner. So the first objective of, or the first reason why do we need modulation is to have practical antenna size. As we can see in the figure here, we have different frequency ranges, and this is what we call frequency spectrum. We have, for example, in the range of 500 to around 1.6 megahertz, we have the range of the AM radio. In a slightly higher range of 88 to 108 megahertz, we have FM radios, and of course we are familiar with those ranges. So these are the ranges that the radio communication systems use to transmit the radio channels wirelessly. Also, we have many other communication systems, such as the TV systems, which use the range of frequencies around 50 megahertz and another range around 200 megahertz. we have what we call the infrared range in the terahertz frequency. We have the microwave range from 300 or 500 megahertz to 300 gigahertz, and you can see here the classification of different bands of a spectrum classified according to their frequency, starting from the very low frequency VLF frequencies to the very high frequency, ultra high frequency, and super high frequencies. And these are the frequency ranges for which the wavelength of the signal is in the range of centimeters or millimeters, which makes communication through a wireless channel possible. So the question now is, what if we don't need an antenna for the communication system? We only need an antenna if we have a wireless communication system. However, in other communication systems where we have wired communication, there is no antenna, and the condition that the antenna size is proportional to the wavelength of the information signal or the signal communicated is meaningless in this case. And definitely we have many communication systems that are still wired, such as the landline phone communication systems. So the question now is, do we always need modulation even if we don't have wireless communication? The answer of this question represents the second reason why do we need modulation. The second reason why do we need modulation is to allow what we call multiplexing. So what is multiplexing? Multiplexing is transmitting more than one signal simultaneously, transmitting more than one information signal simultaneously. So multiplexing is usually needed to allow the efficient utilization of frequency bands. So instead of transmitting only a single signal at a time, we might need to transmit more than one signal at a time. For example, such as in TV systems or radio systems, where many radio channels are transmitted simultaneously, and the user has the freedom to choose which channel or which signal to listen to. So this is called multiplexing, and there are many types of multiplexing that we will study together. But for now, it's important to know that multiplexing is a way to allow the efficient utilization of frequency bands or communication resources in general, which are scarce resources in communication systems, and we don't have the liberty to use them without high efficiency. In order to understand multiplexing more, let's have an example of a multiplexing system in which we perform multiplexing in frequency domain, or what we call frequency multiplexing. Sometimes we abbreviate it as frequency division multiplexing. So let's imagine that we have three signals, and those three signals are all of the same nature, whether these are different voice signals or different radio channels, and they are all in the same range of frequency. For example, here we have three voice signals, or in the range of 300 to 3.4 kilohertz. If we want to use the same communication channel, whether that channel is a wireless channel or a wired channel, again, if we need a wireless channel, then we are back to the first reason, in which we need an antenna, and the antenna size dictates the frequency of the signal. However, even if we don't have a wireless communication system and we have a wired communication system, but we want to use that wired channel to communicate more than one signal instantaneously. If we send the 3 signals at the same time in this form, we will have an overlapping between the 3 signals, because the 3 signals will be transmitted at the same time and at the same frequency. They have the same frequency, they have components in the same frequency range. So there will be overlap and the receiving side will not be able to separate each signal from the other. However, if we perform modulation, and again here we consider the definition of frequency translation for modulation. So if we perform modulation, if we change the frequency of each of those signals such that when we change the frequency of the first signal, we make such a change. When we change the frequency of the second signal, we change it such that it is located at a different frequency range, and similarly for the third signal. Now if we add these 3 signals, since each one of the modulated versions of the signals is located at different frequency range, so they will not overlap. And at the receiving side, if we want to separate them again, if we want to get, for example, signal 2 right here, so we can easily extract it using a band pass filter which selects the signal in such a frequency range and stops any signal in the frequency range outside. So this is called multiplexing, the simultaneous transmission of more than one signal. What we have achieved here is that we used a single communication channel to transmit more than one signal simultaneously. However, for that to be useful, we must have a way to separate them back again at the receiving side, and here we performed frequency division multiplexing by translating each signal to a different higher frequency so that we can separate the signals, the multiplexed signals, using bandpass filters. So again, what we did here at the transmitting side, that frequency translation is a form of modulation as we discussed. So the main question now is, how do we perform such frequency translation, or how do we perform such modulation? Let's start with some basic analog modulation types. Throughout the course, we will study many types of modulation. We will study what we call continuous wave modulation, pulse modulation, digital modulation. So let's start with basic types of analog modulation to help us understand more what is modulation. So in order to understand modulation, let's start with few definitions. The first definition is a carrier signal. We have a carrier signal. Such a signal carries no information because it is a known signal with fixed amplitude, fixed frequency, and fixed phase. And as we will know later, there might be different forms of carrier signals, and these different forms of carrier signals define what type of modulation is being used. However, since we are starting with the analog modulation types, or what we call sometimes the continuous wave modulation, so the type of carrier in this set of modulation techniques is a sinusoidal carrier. So a sinusoidal carrier is characterized by 3 main parameters, and these 3 main parameters are the amplitude, the frequency, and the phase. Of course, if we want to draw such signal, we will have something like that. in which the frequency is fixed, which means that we have a repeating pattern with the same period, does not change with time. We have the amplitude here. The highest possible amplitude is AC, the lowest possible amplitude is negative AC, and theta t represents the initial phase. Sometimes we refer to that as the amplitude, and the whole argument of the cosine function we refer it to as the angle. And later on, when we explain angle modulation, we will know how to differentiate between the phase and the frequency. So for now, it is sufficient to know that for a sinusoidal carrier signal, it is characterized by an amplitude and an angle, and this angle has two components, which are the frequency and the phase. The second signal that we have is the information signal itself. And this information signal, m of t, is any function of time. Of course, we remember that the definition of a signal is that it is a function, an amplitude which varies, and that variation is with respect to time. This is what defines a signal. An information signal is a function of time. So this information signal, we call it the modulating signal. Now you can guess how modulation might happen. Remember, the definition of modulation was changing one or more of the characteristics of a signal. That signal is the carrier signal. And what are those characteristics in the example we just mentioned? These characteristics are either the amplitude or the frequency or the phase. So how do we change these characteristics? By the modulating signal, by the information signal. So as a result, we have a modulated signal in one of these two forms. In the first form, we have the information signal, the modulating signal, appearing as a part of the amplitude of the sinusoidal signal. We still have a cosine signal here, a sinusoidal signal here, but its amplitude or the magnitude right here is not a constant magnitude anymore. So we don't have these peaks all aligned at AC. No, that amplitude is now time dependent, and such time dependency is in proportion to the information signal, m of t. Similarly, we might have the information signal included in the angle of the carrier. In this case, we still have the amplitude fixed. However, the angle became varying in accordance with the information signal, and that's why we might see a change in the frequency with time, or a change in the phase with time, according to how this m of t is included. These two expressions give us the two main types of analog modulation, which are the amplitude modulation, or abbreviated as AM, in which the information signal, the modulating signal, modulate the amplitude of the carrier signal, and as a result, the modulated signal is in this form. And the other type is angle modulation, and this angle modulation, since the angle includes frequency and phase, so it might be classified as frequency modulation, FM, or phase modulation, BM. Of course, you can recognize that AM and FM are very known expressions, especially in radio communication systems. So again, in angle modulation, the information signal is included in the angle of the carrier, so that the angle of the carrier signal is changed or is varying in accordance with the information signal. as we have seen at the beginning, in the top figure here, you can see that we have a sinusoidal signal whose frequency is constant. And in order to see that, you might look at the zero crossings. So as you can see here, the time between zero crossings is fixed, so the frequency is constant. However, the amplitude, or the envelope as we call it, is not fixed, it's varying, and this variation is what we call information, or what we consider the information. In the second example, while you have the envelope almost constant, we can see it almost constant, but the frequency is varying, as you can see here from the zero crossings. In this part of the signal, as you can see, the time between different zero crossings becomes less, which means the frequency is higher. Of course, you recall that frequency is inversely proportional to the rate of change, and back here you get an increasing period, which means a decreasing frequency. So you can assume, or you can say that in these parts, the low frequencies correspond to low amplitude of the information signal. In these parts, you have high frequency, which corresponds to high amplitudes of the information signal, and so on. So that's why we say that in this case, for example, the carrier signal carries the information in its frequency. So how do we study different modulation techniques? In order to study different modulation techniques, you need to know how to mathematically express the modulation techniques, as we just see a few examples of angle modulation and amplitude modulation. And as we can see, even though there are many variations of amplitude modulation techniques and angle modulation techniques, so we need to know the mathematical expression, and these mathematical expressions differ from one modulation technique to the other. Also, modulation techniques differ from each other in the bandwidths, the frequency range, and we will study together what is meant by bandwidths. They differ in the transmit power, and these two parameters are considered the most important resources in communication systems. That's why it is very important to study the bandwidths and the transmit power after the processing that we do at the transmitter, or after modulation, in order to compare modulation techniques to each other. And then we need to know what is the complexity of processing that is needed to perform the modulation process and the inverse process at the receiving side, which is the demodulation. So we need to know how will that modulation technique be implemented, what will be the modulator and what will be the demodulator. And again, this represents the complexity of hardware. So we might have a modulation technique which is efficient in power and efficient in the bandwidth utilization, but it is complex in implementation. So it is important to study how the modulators and demodulators are implemented. And finally, we have the applications, different applications which use different modulation techniques. As we mentioned a while earlier, in radio communication systems, we commonly use the amplitude modulation and the frequency modulation as the modulation techniques. And as we study different modulation techniques, we will study different applications which use those different modulation techniques. So that's all for our first introduction about modulation. So we studied, or we explained together, what is modulation, what is the general definition and the most commonly used definition of modulation. We mentioned why do we need modulation, whether we have a wireless communication system or even a wired communication system, when do we need and when we don't need modulation, and finally we introduced the basic idea or the basic types of modulation techniques that will be discussed in detail in subsequent lectures.